Up for George. My name's Rick Koskela. I live in Cave Creek, that's up north here in Phoenix area. I recently moved from Chicago, Illinois. How did I get involved in this and why am I here? Well, my brother-in-law happens to be a race car driver. And stock car racing is extremely competitive. There's multi-millions of dollars being spent to go fast, win races, get your sponsor put up on TV, billboards, et cetera, et cetera. Some teams have a budget of in excess of $10 million to spend. Now this is strictly stock car racing now. You may have heard of the Daytona 500 or races like that. Some of the popular drivers, maybe you might recognize their names, Dale Earnhardt, Rusty Wallace, people of that nature. Anyway, my brother-in-law has been involved in racing for many, many years, and he's one of the underfunded teams. He's getting on up in years, and big corporations want to give money to young, handsome guys who can go fast and attract a lot of interest from the youth that are following the sport. As a consequence, throughout his career, he's basically not received major sponsorship money, and he has to make do with hand-me-downs, so to speak. 1 year's technology, he'll get the next year. And the other guys have it, in 1996, he'll get 1995 technology, et cetera, et cetera. And there's a continual race within a race to go faster on less money. These people will spend $50,000 trying to squeak 10 extra horsepower out of a race car engine. And why would they do something like that? Well, give you an example. Just this past Friday, they qualified for the Pennsylvania 500, which will be run this afternoon. And how they qualified, typically they'll qualify in 2 sessions. First round, the top 25 or fastest 25 drivers are locked into the race. They can spend the rest of their time preparing the car to actually race rather than to qualify. And this past Friday, for example, Dave Marcus was the 25th qualifier. He went 2.5 miles around the track in 54.111 seconds. And then the 26th qualifier was Darrell Waltrip, went around the track in 54.112 seconds, a thousandth of a second. And now he has to try to requalify for the race, thousandth of a second. Well, what does that mean in practical terms? There are 46 cars that attempted to qualify for this race, and there are only 43 positions that will be allowed to race. But in this first round, for example, only 25 are accepted. Out of these 46 cars on that first round of qualifying, the fastest car went around a 2.5-mile track in 53.316 seconds, and the slowest car went around the track in 55.468 seconds. That's a difference of 2.152 seconds. Doesn't sound like much. Let's make it more real. Let's use an average speed of 166 miles per hour. That's kind of a median speed between the fastest and slowest. You end up going 2.766 miles in a minute, or 14,607 feet ad nauseum, down, 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 down we go. It turns out to be 0.2435 feet is a thousandth of a second. That's 2.92 inches. So this fellow, Darrell Waltrip, has to requalify because he was less than 3 inches behind the guy in front of him. Another example of how competitive this sport is, the whole field of 46 cars was separated basically by 20 feet over a 2.5-mile course. So you can see that spending $10 million to get you another 2 or 3 inches in front of the next guy assures you a place in the race. Or you're on the hook. You drive home and you wait till next week. Well, anyway, getting back to my personal involvement in it, my brother-in-law is not as endowed with money as some of the major teams are. So I thought, well, I had been investigating Tesla technology for a while. I was interested in the Tesla pumps. And I thought, well, maybe we can apply a Tesla pump to the race car in some fashion. I started educating myself about the race cars and the type of equipment that are used on them. And it turns out that, as most technology is, everybody tries to get higher and higher tech at all times. Oh, this pump will pump more water. This pump will pump at a higher pressure. This will do this. This will do that. To show you the way the pump works, actually, this is a casing of a General Motors water pump, and it's a typical impeller, a bladed impeller, sits in the pump in this manner, and it's driven on a shaft from the front of the pump, and it throws the water out into the block of the engine. Well, people go to great lengths to try to pump more water for some reason. Look at this CNC-designed aluminum impeller. Here's a CNC-designed aluminum impeller. Costs a lot of money to do this, just to pump more water at a higher pressure. And my question was, why? What's the point? It'll become obvious in a moment. I'll pass these around. You can take a look at them if you like. These are, the small one is a standard impeller, and the other one is a CNC machined impeller. Anyway, it turns out, if you know anything about stock car racing, or if you don't, they've tried everything to go faster. They'll try anything they can think of. They'll cheat if they can get away with it. There are examples of drivers putting 20 pounds of buckshot in the doors with a little hole, and they pull a string, and while they're racing, the buckshot drops out of the car, and it becomes lighter, and they go faster. I mean, hollowed out frame rails with extra fuel. You name it, they've tried it. I thought, well, why don't we try something with technology that might aid in using the horsepower available in a race engine to go faster. And here's how I went about doing it. It turns out that the race teams have found through the years, when they're going really fast through the air, if they use a standard water pump, it pumps too much water. It pumps it too fast through the radiator. So their quick solution to the problem is to restrict the output of the water pump, to slow the water down going through the radiator so it'll be able to cool more adequately. I thought, well, what's the point? Now you have this powerful water pump trying to jam this water through this smaller opening. You're wasting power. This is power that could be used to make the car go faster. In the case of Darrell Waltrip, if he had 1 extra horsepower, I'm sure he'd be really happy about it. He'd have made the race on the first day instead of having to try to requalify on Saturday. So getting back to the Tesla technology, I decided I'll fool around. I've got a little a lathe and a mill in my basement, and I've been a tinkerer most of my life. I'll fool around and I'll start trying to make some Tesla pumps. And you have to crawl before you can walk, walk before you can run. So let me pass some of these around. You can see just samples of disc impellers I made, riveted together, bolted together, and then finally made out of a billet of aluminum. It turned out that the first Tesla pump I made for a race car was put together with rivets, and after about 3 laps, it fell apart. The rivets just broke on it. It couldn't stand the centrifugal forces of the rigors of racing, so to speak. I ended up literally having to make the impellers that were finally used in a race car out of a block of aluminum, and I'd put it on a rotary table, spin it around, use saws, literally cut the slots with a saw, cut inlet ports with a milling machine. I'll pass some photos of various stages here of development of a billet type solid impeller for you. After I had the experience of the impeller breaking and making the solid impellers, then I started experimenting with the various diameters and disc spacing with the pumps. Now, a question came up earlier before I started here. Well, how efficient is your pump? what have you done to increase the efficiency? What's your design parameter, et cetera, et cetera? Well, I'll tell you that this pump was designed not to be efficient, or to be as little efficient as possible, to be only as efficient as needed, so that any other extra power that was generated by the race engine would be put on the ground so the car would go faster. There's no point in wasting energy trying to pump 10 pounds of you-know-what through a 5-pound bag. As an example of that, for this Ford pump, I designed a bladeless impeller that was originally, as you can see here, maybe you can't, but it was originally this overall diameter here. And it pumped quite well. It worked well, cooled the engine properly. And the guys told me, look, why don't you cut it down a little bit? It'll pump less water, but it'll take less power, and we can go faster. Let's cut it down to the point where it no longer, or it's right on the edge of cooling properly for the race car. And we brought it down to this size, and we found that this was about the optimum size for an impeller for a Ford NASCAR race engine. Hence, it's not as efficient as it could be. The same thing goes for the General Motors pumps. They were cut down purposely to be as inefficient as they could be, but only as efficient as they needed to be. It turns out that when set up in that configuration and measured on an actual dynamometer, and these guys have $1 million dynos, and they spend lots of money on this stuff. They've literally measured a 2 horsepower net increase if they use a pump like this. Now, I cannot attribute 2 horsepower increase to simply using a Tesla pump, because the pump is running less water through the motor. It's doing less work. Therefore, you would expect it to use less power. And that's exactly what happens here. In fact, Tesla pumps, I believe, to be very inefficient at low RPM and low diameters. I believe the aerodynamic rule of doubling the RPM will quadruple the aerodynamic drag. That's a theoretical situation that the Tesla pump is supposed to work under. I didn't find that to be true. When I tested the pump, I jerry-rigged a little situation. I had an 18-gallon tank of water, and I would time how long, literally, it would take to fill this tank of water at various RPMs. And I know that's a real low-tech solution, but if you don't have all the measuring equipment, you have to make do with what you got. I found that the stock pump climbed up at roughly a 45-degree angle here. The fastest I was able to pull this pump with a little 2.5 horse motor was about 3950 RPM. I was able to pull the Tesla disc pump all the way up to 6,000 RPM, and I noticed that the pumping efficiency did tend to increase with RPM. Now, I think that the reason we didn't see this exponential pump efficiency change was because, number one, we're at a very low RPM relative to the other pumps, and disc spacing has something to do with it. If you have the disc space too wide, the boundary layer effect only occurs near the discs, and there can be backfeeding of the water in between the discs, et cetera, et cetera. Be that as it may, it still pumped enough water to adequately cool a race car. So they went ahead and put it on the race car and used it in 3 Winston Cup races. And they've used it to qualify quite a few different times. In case you're interested to see how it pumps, that's my little jerry-rigged situation there with a 2.5 horse motor, and that's a General Motors race pump there. It pumps quite a bit of water, as you can see. The pumps can be made out of just about anything, I've found. I happened to start out using hard drive discs from computers. I found them at a surplus store, little aluminum discs of various sizes. I haven't made any with the larger discs yet because the hole is a little larger than I'd like. Anyway, I guess that's about all I have on the car racing pumps. If you have any questions, I could perhaps answer some for you. And then I've got a swimming pool pump here that I put together 2 days ago. Since I moved to Phoenix, I know there are so many people here who have swimming pools. I thought they're running swimming pool pumps continually or nearly continually, and they're spending a lot of money doing that. Their electric bills are quite high because of it. So I thought, well, I'll start experimenting with a Tesla pump to see if perhaps it would adequately circulate the water in a swimming pool and do it at perhaps a lower cost. And we'll see if we can crank this up here in a few moments. I have to manually prime it. It's not a self-priming pump. Like I said, I'll do that in just a moment. And then after we do this pump, in case there are some of you out there who are interested in electric motors, this has nothing to do with Tesla pumps now. I happen to have found an interesting configuration of electric motor that some of you experimenters might be interested in. It's a flat or pancake type motor that has quite a large amount of torque for the amount of current that this motor uses. Could I get somebody maybe to plug this in after I prime the pump, so to speak? There's an extension cord there. I'll also disassemble this afterwards, and you can see what a testament to poor design this actually is. Actually, I suppose we should have the Let's Go Out to the Lobby song, and people can have an intermission now, huh? The dancing hot dogs on the screen.
Biohazard waste basket.
Oh, I thought that was an appropriate basket here, biohazardous waste.
Plug that hole in.
Yeah, I've got a plug here.
I'll get a shower this morning.
Oh, you won't get a shower. I hope not. Go ahead and turn that on.
Okay.
Yeah, plug it in. You can see that that's pumping a fair amount of water. It's not as much as a standard swimming pool pump impeller would pump. You can pass this around too. This is a standard pump that's inside most of the swimming pool pumps. Everybody see that? And we'll shut it off here so we don't flood the carpet. As you can see, it pumps a reasonable amount of water. Seen enough? Okay, we'll pull a plug on it. And I'll drain this thing out and show you, like I said, the testament to poor design. It shows you that even a poorly designed Tesla pump is going to pump a lot of water. Any of you who are interested in the electric motor, why don't you come on up here too? Is that something you need to see? Oops. All right, here's a story on this motor. I went to a place in Chicago called American Science and Surplus, And it's the kind of place where you walk in, and there are bins of junk. And you walk through there, and you have to spend money. You can't walk out of there without spending money. And in a bin at this one time happened to be these flat motors. I was looking for a motor at the time to make a little motorbike for my daughter to ride on. I was cheap. I didn't want to spend $100 buying one of those things. It turns out that the motors have a flat magnet inside. There are 6 poles on it. And you can buy these motors with rare earth magnets as well. These are ferrite magnets. They're fairly powerful. And the armature is interesting in the sense that there's no iron in it at all. It appears to be, maybe it's plated copper that's been etched. Okay? You can see the windings etched on this armature. The armature's less than 1/16 of an inch thick. It's just a flat armature. Okay? It's an interesting way to manufacture. I don't know how they do it.
Who is the manufacturer?
The manufacturer of this motor is Permanent Motion Technologies, PMI. It's a division of Kohlmorgen Corporation. U.S. patent number, blah, blah, blah. Yeah, you can come on up and look at it if you like. But again, here, I'll pass this around if you want to look at the armature. There's an additional magnet on here because I'm kind of experimenting using double the magnetic strength. But anyway, this happens to be a 12-volt motor. Now, I've got one that's running here, and you notice there's a little metal pin through here. It was obviously to attach some gear or something to that effect. I brought a little 12-volt motor along, battery along. I'll turn this on, and you won't believe how strong this motor is. All right? I got a piece of wood here. Watch this. I'm pushing pretty hard on this. You know, for people who experiment with motors, if you want a high torque motor that uses relatively low current, this is the way to go. I don't know where to obtain them other than surplus, or you can try to contact this company, but I would suspect that a rare earth magnet type form of this motor would probably be fairly expensive. I spent $6.50 for it at a surplus store. This is just how it came out of the box. $6.50 surplus. I mean, this is really a powerful little motor.
What's
So
the speed on that?
I don't know. I've never measured it, but I would imagine it's probably 2,400, 3,000 RPM, something like that.
Speed by varying the voltage?
Sure, sure.
Are you going to be hooking up to your daughter's?
No, I did in fact make a little riding motorcycle for my daughter, and it went pretty well.
Does it fill anything?
Oh yeah, it'll go up slight grades. Let me take apart this water pump while you're looking at that motor, and then we'll end the talk here. In fact, let me run outside to dump the water. Okay, this ought to be adequate. Like I said, my brother-in-law is a race driver, and I was trying to think of ways to help him go faster. Destroying the equipment here. Now this, the impeller in this swimming pool pump, I just took a piece of junk aluminum and a couple of these hard drive discs and a few bolts and nuts. I considered nothing in making this other than making what looked like a Tesla impeller. The spacing wasn't considered at all. I just, whatever the size of the bolts were, that's the spacing between the discs. Okay, here's the impeller that was used in that swimming pool pump. You can take a look at it. It's just hard drive discs, like you saw on the table, bolted together. Nothing sophisticated whatsoever in there. And one thing I'd like to point out is that there is no labyrinth seal on the end of the pump. If there was a seal on the end of the pump as Tesla specifies, this would pump at least 3 times as powerful as it does now. What happens in this particular case is when the discs sit in here, the pumped water can leak back around into the inlet of the pump and just circulate around in there. So the efficiency is very low. And you can see it was pumping quite well for as poor as the efficiency is of this pump. Probably next week when I get a little free time, I'll make a labyrinth seal for it, start testing. Well, that'll about do it. If you have any questions, I'll be glad to answer them. I know George wants to get his demonstration underway in his talk.
How would you make this? With this particular pump?
This pump here,
Yeah, I mean,
I'd probably replace this piece and then make this flat rather than conical. You can see this is made to match the contour
right,
of this impeller.
right.
I'd probably make this flat, and I'd also probably extend a little pipe right into the inlet portion of the pump. And also cut little grooves in it to allow water to spin around and cause that labyrinth seal effect that he's talking about. Pardon me? Oh, these were just saw blades I brought along to show people how one might make a solid impeller. I literally had this on a rotary table and had a mill going in, spinning this saw, and literally cut the discs out of a solid piece of aluminum.
That's kind of a saw that you use, though, something like that?
Pardon me?
You use something like this to make that?
Yeah, I used this to make that.
Wow. That's pretty cool. And is there a problem with getting too wide?
If you get too wide on the discs, I'm sure at some point it won't pump anything, or very little. You can see the impeller I passed around that was in this swimming pool pump. There was, again, no real consideration to the viscosity of the fluid or anything. I just threw it in there to see what would happen. And you can see it pumps fairly well for having literally no design other than it looks like a Tesla pump.
Did you make this or
No, I took that one apart and took a magnet out of another motor and put it here. So I wanted to experiment with a magnet on both sides of this armature. The way this motor comes standard, there's only one magnet, and the armature sits along the side of it. The poles are shown using the case here. I haven't finished testing it yet, but yeah, a work in progress. I just thought I'd bring it along because it's an interesting motor, and a lot of people are trying to find the, latest and greatest stuff. $6.50, yeah, it's cheap.
It's been surplus in somebody's research.
Mm-hmm.
Now, these are all 3 part of the same deal?
Yeah, that's how the brush configuration is. There are 6 poles, if you look at it, 6 poles here, north, south, north, south, north, south. They're just selling these cases for $2.50.
Where did you get that one?
I got that from a place called American Science and Surplus in Chicago. I believe they have a web page. I don't know.
Scientific, science?
American Science and Surplus. It's on Northwest Highway in Chicago. I believe they have one in Milwaukee, Wisconsin as well. Yeah, they've got all kinds of stuff at that place. Actually, when I saw a box full of those motors, I snarfed them all up. Hopefully, they'll have some more. I got about 6 or 7 of them, so.
Yeah. I have a
Any other questions,
Yeah,
or-
I got a question,
Sure.
or a comment. Where I live is in Idaho, and they have potatoes.
I can't hear you.
Okay, well, is this going? Okay, I said where I live is Idaho, and they have potatoes.
Right.
And they have those slurry pumps all the time.
Uh-huh.
And there's a Tesla, they have a model there, and a water tank, and they're manufactured commercially.
Uh-huh.
And they use them out where I live all the time for the potato slurry, because see, they won't take on a rock, and, you know, the potatoes get ground up and stuff, and it will still pump it, you know, a fairly, you know, liquid situation, but solids in there, and rocks and all kinds of stuff, and so the turbine pump is commercially made. I think it's in Chicago or somewhere, and in the area I live in, they're commercially used.
Yeah, I know there are a
And-
few
and
companies that are doing
Anyway, I
that.
was just going to say, and several years back, some guy brought a whole bunch of those hard drives in and was selling the disk and everything. I've seen it done before with air and liquids, but there is a commercial application of the Tesla pump, and it is manufactured, and it is used in industry all the time.
Yes?
There's a guy that has a patent, he's out of San Diego, he buys the motor and the drive from Powell Pumps, and he manufactures them. I've got the catalog on them, they're commercially available, they're used for
Uh-huh.
pumping live fish.
Yeah, if you do any reading about Tesla pumps, they're really quite extraordinary. Even, well, in the case that you just mentioned, pumping live fish, that would be a very low-speed operation, you know, because you wouldn't want to hurt the fish. But again, they don't even literally touch much of the discs as it's.
Pumps are actually running at 1,800 RPM, but because the pumps work by a boundary layer phenomenon,
Right.
and there's a transition from the velocity the fish might move and the velocity of the blade, the fish stays away and the blade does not impinge or hurt the fish.
Right. Well, there's always a certain amount of possibility for impingement. For example, in the typical type of Tesla impellers that you see that are made with hard drive disks, they have to be secured in some way. So if you look in there, you can see a shaft or a spacer of some kind, and that will usually bump into a fish or a blood corpuscle or whatever it is that you're attempting to pump. For these solid billet ones, obviously, you can see, if you look close yourself, I mean, if this was spinning at a high RPM, this flat portion here would hit whatever it is you're trying to pump as well. So there's going to be a certain amount of problem. Uh-oh, it's raining here. Certain amount of problem with, you know, trying to pump cornflakes or whatever. You're going to get a certain amount of dust out of it, but all in all, a boundary layer pumping phenomenon is actually a pretty good way to go. Any other things I might be able to add? I mean, strictly from a practical standpoint, because theoretically speaking, I'm sure everybody who's been deep into this has statistics and curves and mathematics for you. I don't have that here.
You have a curve there, what are you showing on the
This particular curve was, again, with my jerry-rigged little situation with the 2.5 horse motor pumping water into an 18-gallon container. I literally took one of the floppy disks and put holes in it and had an infrared LED and a sensor hooked up to a frequency counter so I could determine what the RPM actually was, because I didn't have a tachometer. It's kind of a jerry-rigged homemade tachometer. And I ran the engine at various RPMs and measured the amount of time that a standard pump would take to fill 18 gallons versus a Tesla pump. And again, the results were pretty much what I expected. The bladed pump would pump a lot more water because it's more efficient at low RPM and low diameter. But basically the reason I did this was to provide my brother-in-law and people in the racing industry an idea of how much water would go through, because they're not willing to try anything new on a $50,000 or $100,000 engine unless they know that it's going to be approximately in the parameters that they need. You know, there's no point in trashing a $100,000 motor on a $100 pump. Any other questions I might answer? Or confuse you with?
Yes, when the water comes out, it come out the center of the shaft. How do you, it comes out the center of the shaft?
No, when you're pumping, the fluid being pumped exits at the periphery of the discs. It enters in the center. What you're talking about is if you're using it as a turbine, being driven from the periphery, then it exhausts from the center.
Okay, what do you have to, it does come through the side, the pressure's going to come out through the side.
Yeah, in this pump, for example, the one with the open back, I don't know where this clip is for this mic. We're going to have to look around for it. But as you can see here, when this rotates, there we go. When this impeller rotates, the inlet to the impeller is in here on the front side of the disc. The water is literally spun out in a boundary layer manner, swings out here, and then is fed into the engine block. You can see on race cars as well, they're so paranoid about water flow, they literally modify the standard pumps. Here's a standard pump body, and you can see it's had fittings heliarched into the sides, and they run this to the back of the block and feed water into the back of the block to make sure they get adequate cooling throughout the block of the engine. Any other questions? Actually, in this particular case here, there's no O-ring whatsoever. The only sealing that's happening between the input and the output of the pump is the face of this disc up against the face of the pump. In the case of the GM pumps, for example, and I think I show that in some of these pictures. In fact, you can come up and take a look right here. This has a tapered face, and I put it on a mill, and I just made the tapered face flat, so that the disc has an area of what I would call interference. I don't have a labyrinth seal in there. It's just an area of interference where it's trying to pump water out past that, and any pressure that's trying to come back in alongside of it is kind of canceled out. Pardon me?
A water seal.
Yeah, pretty much a water seal. And, you know, you could get crazy, and you could spend a lot of time making labyrinth seals, but for what? The whole point here was to make it only as efficient as necessary to cool the engine for a certain parameter of racing. This wouldn't work well, in my view, for your average car on the street. Why? Because you're driving at slow speeds. The pump is turning at slow RPM. And a Tesla pump is much less efficient at low RPM and small diameter of the impeller. But the race cars, they're going flat out all the time. They're full speed. The pump's turning around 6,000 RPM all the time in a race, or in a range of, let's say, 4,500 to 6,000 RPM. So it's at its most efficient speed regarding the Tesla pump. Well, with that, I'm going to close up here, and George can start setting up to do his little talk. And appreciate your attention. I hope I was able to give you some useful information.
Business card?
No, I don't, but I'll give you